agreeing to be here and to present your work. I think it's very exciting, especially that I did some work on survival analysis as well. So it's very, very interesting for me to hear. And so you are a fourth year PhD student at ETH Zurich and University of Zurich. And you are particularly interested in right sensor data analysis for cancer research. So that's all to you now.
Yep, awesome. Thanks a lot for the introduction, and thanks a lot for having me. Okay, let me share my screen. Okay, does that look okay? Can you all see that? Can somebody maybe, because I don't see the chat right now, so maybe somebody can just
it's all
confirm.
good.
Okay, all good. Okay, perfect. Okay, yeah, so thanks again for having me. So I will be talking, so the title is officially sparsesurv, which is our recent paper on a software package for fitting sparse survival models. But since this is a longer seminar, I'm actually going to talk about both this project and another related project on multi-omics survival analysis.
I'm very sorry. I just need to ask if everybody's okay that I'm going to record the session.
Okay. Yep. Okay. Okay. So just a couple more words about me. So I did a master's in statistics in Zurich, and as has been mentioned, I'm now doing a PhD shared between two labs here in Zurich. I mostly work on two things. So I mostly work on one is survival, as has already been mentioned. Kind of broadly defined. These days, I'm working more on interpretability, but this kind of work that I'm presenting today is more focused on high-dimensional data, so more applied omics data for survival. And then the other thing I work on is more in my other lab, and it's focused more on bioinformatics. So this is more the analysis of and methods for long-read RNA-seq data. And I'm actually spending more and more time these days also focusing on long reads, but I'm still very interested to chat about survival and multi-omic survival. So if anybody wants to chat afterwards, I'm happy to talk. Okay, so getting into the talk, I from what I understood, the audience is somewhat diverse. So I thought I would just give a quick introduction background. So kind of just quickly covering general, what is survival? What is this kind of omics data that we deal with? What does multi-omics mean? Just to make sure that everybody's on the same page. Afterwards, we'll get started with the first package, or the first project rather. So this will be sparsesurv, a Python package for fitting sparse survival models via knowledge distillation. This will be taking up about 15 to 20 minutes. And I will already mention here that both the first project, so sparsesurv, and also the second project are joint work with Nikita, who is in my lab at ETH, and who's also jointly affiliated with IBM here in Zurich. Right, and then the second project I'll be talking about again for about 15 to 20 minutes will be SurvBoard. So this is a standardized benchmarking framework for multi-omics cancer survival models. And then I have a short outlook, not so much a summary, but more where do we think these areas are going, like multi-omics survival, but also this unimodal high-dimensional survival. Okay. Getting a bit into the background. So what is survival analysis, right? So the way I see it is that in survival, we're interested in modeling some strictly positive random variable t. And although there are multiple things we may be interested in doing inference on or predicting, the primary estimation target, as far as we approach survival, is generally the survival function, which is really just the probability of surviving beyond some time t. Thus far, this might sound sort of trivial or maybe not so different from the data you otherwise typically work with. But most of the time in survival, and this is really more or less characteristic also of survival data, is that you never really have fully observed data. So there's really two main schemes that occur with this type of time to event data, as survival data is also called. Namely, first is truncation, which really just means that, okay, we only observe data under certain circumstances, and the typical.
Sorry, David, I think you stopped sharing the slides.
Oh, okay. Well, that's odd. Yeah, somehow it broke off. I didn't click anything, but okay. Is it back?
Yes.
Okay, perfect. Thank you. Right, so as I was saying, the first is truncation, which really just means that data is only being observed under certain circumstances. And a typical example here is that in a microscope, molecules only show up if they're larger than a certain size. So this would be an example of left truncation, which means that you only observe data that is larger than a certain minimum size. And you can construct similar scenarios for right truncation and interval truncation, which really just means that instead of having a cutoff at the left, you have a cutoff at the right, meaning you have some maximum, or in the interval case, you have some interval in which you observe the data. And then, of course, when you do inference, you need to account for this truncation somehow. The actually even more common scheme is censoring. And once again, we have right censoring, left censoring, and interval censoring. And here, instead of only observing data, we only actually have data that is only available from, until, or in a certain time. So I will give an example here with right censoring, because we deal mostly with observational cancer data, and there we're dealing almost exclusively, or we at least assume to work almost exclusively with right censored data. And so here's some toy data, and we basically have 10 patients, and each of those patients we follow from time 0, and then we follow them until either an event occurs, which in the cancer case would be death, or censoring occurs. So for example, for patient 8, we see, okay, at time roughly 20 here, an event, meaning death, occurs, whereas for patient 6, we see that we observe them until about time 55, but then a censoring event occurs, which means that, okay, at time 55, for the purposes of us, they actually basically just drop out of the study, and the only information we have is that they were alive at time point 55, but not what happened to them afterwards. Again, of course, you want to incorporate this somehow into your modeling framework, and this is really the main thing that survival models then incorporate. And that typically you also have certain assumptions on the censoring and how it relates to the survival random variable, but I will get to that later on. Okay, so I will, throughout the talk, denote the random variables corresponding to the time of event and the time of right censoring as T and C. And here are some common relationships between survival objects of interest, right? So I've already shown the survival function. What's also a common quantity in survival is a so-called hazard function. So this is this lowercase lambda. This is not the most interpretable quantity, but you can roughly think of this as being an instantaneous risk of experiencing the event. And you can get the hazard function also as essentially the density over the survival function. So this part is actually not so interesting, mostly because we rarely kind of try to estimate the density function. But what is interesting is actually that often we actually don't estimate the survival function directly, but instead estimate it as the negative exponential of the cumulative hazard function, which is really just the hazard function integrated up to some time t. In particular, a lot of the models that we'll be dealing with today, most prominently the Cox model, actually don't estimate the survival function directly, but typically estimate the survival function via the cumulative hazard function. And just getting back to assumptions, again, we won't get sort of very theoretical or technical today, but just so we kind of have it clarified, the two main assumptions in survival, as far as most methods go, they're not required for every method, but for the purposes of this talk, we can just assume that they hold, are conditionally independent censoring, which really just means that these two random variables T and C are independent and conditional on X, and then also non-informative censoring, which is a bit of a more technical assumption that you need for the likelihoods to work out the way that you want them to, which really just is that C may not be a function of any of the parameters of T. So basically, they cannot have any parameters in common. Okay, getting to some of the methods that we'll be talking about today. So the most common one is arguably the Cox model, also called Cox proportional hazards model. So in the Cox model, we actually parameterize the hazard function, as I've mentioned. And in particular, we actually don't parameterize anything to do with time. So we just assume that we have some baseline hazard, lambda 0, which is a function of time. But our estimated quantities, in particular this beta, actually doesn't interact directly with time. Instead, we just multiply this baseline hazard, lambda 0, with this exponential x beta, but the beta never directly interacts with the time. And the Cox model is called proportional hazards because suppose you have some continuous variable x1, and essentially you want to know the effect what happens, say you increase your x1 by exactly 1, then the impact on the hazard function is exactly this exponential beta 1, hence proportional hazards. Personally, I think this hazard function formulation is nice, but it can be a bit hard to visualize what this actually means in terms of the survival function. So personally, I always try to look at these survival functions. And here are some examples of survival functions generated using a proportional hazards model. And in particular, what this proportional hazard assumption means is not only that it is in effect that the hazard functions of two patients can never cross, and that in turn means that the survival functions can never cross. So you see this, I think, illustrated quite well here, namely
Sorry,
that.
David, I think it happened again, the slides.
Okay, oh, that's very odd. I'm not sure why. Should I? So I'm on the browser. Let me just put my pad out. I'm on the browser. I'm not sure why it's stopping. Should I try to maybe just share the presentation? Okay, this doesn't work. Okay. All right. Okay, does that still work now?
Yeah, it works. Mm-hmm.
Okay, maybe I'll just stay in non-presenter mode. Maybe that way it's. Okay, right. So that's the Cox model, and I mean, you can really think of this in an interpretable manner as just thinking that, okay, if a patient has a lower survival probability at time 50, they will always have lower survival probability than another patient at every other time, right? So I guess that makes sense. There are also some other more flexible semi-parametric methods. So one that we personally find quite interesting is the extended hazards model. So you keep the same term x beta here, but you add an additional x gamma that interacts directly with the t here. And in particular, this is an interesting model both theoretically and from an application perspective, because it actually recovers the Cox model and also other semi-parametric methods as special cases. So in particular, if you just set this gamma to 0, you recover exactly the Cox model, right? Because this term goes away, and then you end up with exactly a Cox model. The extended hazards model does not have this restriction of the Cox model. So in particular, you're not restricted to non-crossing hazards, and thus also not to non-crossing survival functions. So you can get survival functions like these, right, where maybe the red patient has a lower survival probability than the blue and purple patients early on, but then later on it actually he has better survival probability than these two patients, especially like after time around 160. There are also fully non-parametric methods for survival. So some that we'll be dealing with today, or at least in passing, is random survival forest. There's also some methods that I'm not really touching on, like fully discrete time methods. But these methods are generally pretty similar to their non-survival analogs. So random survival forest, you can really think of as very similar to let's say, a regression random forest. So you have some splitting criterion that you split your tree with. This one is, of course, also adapted to survival. And then once you're in your leaf node, which is indicated by the dependence on x, you then fit a fully non-parametric survival function estimator. This is Kaplan-Meier in this case, at each leaf node. And since it's not fully non-parametric and really is only determined by which leaf node each sample gets put into, again, going back to the survival function example, a random survival forest has no such restrictions, right? So you have no restrictions on not crossing at all or crossing a certain number of times. You're essentially fully flexible there, and you can cross more or less an arbitrary number of times. Okay, getting a bit towards evaluation. So a couple common performance metrics in survival are, first is interlinear concordance. So this is a typical concordance measure, right? So basically higher is better, and a random prediction would be 0.5. Sorry, this is a bit somehow cut off. And really what you're doing is you're just evaluating the fraction of comparable pairs that is correctly ordered, right? When I say correctly ordered, I mean something like essentially you want a patient that in the end ended up experiencing the event earlier. You want that patient to have received a lower survival probability than another patient that experienced the event later. Decalibration is a newer metric that's more from the machine learning side. And I don't really have a formula for this since it's a bit more convoluted to calculate, but you can really think of this as an analog to these typical calibration metrics, like the expected calibration error, to a survival analysis. So they don't try to evaluate, they're essentially fully orthogonal to something like the concordance. So they don't evaluate discriminative performance at all. They're essentially fully focused on the calibration of the survival probability, meaning is the survival probability that's estimated actually meaningful? Does 90% actually mean 90%? And then lastly, we have the integrated Breyer score, which is, again, I think probably most of you are familiar with the Breyer score. And this is really just an extension of the Breyer score to the right censored settings. Then you just integrate it typically just integrate it across the full survival space that you're interested in. So typically from 0 to some max observed time. And again, this means that lower is better. Okay, now we're going briefly away from survival and just a few words about the data, and then we'll start actually getting into some of the results. So the most important data type for... Sorry?
It dropped again.
Did the presentation cut out? Oh, it's so weird. Okay. I don't know what's going on. Can I try anything else? Should I try rejoining or...
I don't know. It's like good as long as it's good. So sure, maybe
okay.
Is it like some specific time?
Okay.
Hard to say.
Okay, maybe I'll just retry. Okay. Right. So RNA-seq will basically be the most common data type for today. So for those of you that are less familiar, right? So humans have a genome, and in turn, this gets transcribed to a transcriptome. So you have some number of genes, so about 20,000 protein coding genes, more like 50 to 60,000 if you're not limited to protein coding. And in RNA-seq, what you observe is these typically these very short reads, right? And what we then do is we try to assign these reads to a gene, and then we end up counting the number of reads that are assigned to each gene. I mean, it's simplifying quite a bit just because this is a whole research field as well, but for the purpose of today, that's kind of all we need. And then we end up with something like this, right, where we have a patient by gene matrix, where for each patient and each gene, we get some number that reflects the abundance of that gene in that patient or in a sample of that patient. And the hope is that this expression recapitulates something about the condition of that patient. So in the cancer example, we would hope that maybe patients that have good prognosis show higher expression for some genes that may be associated with good prognosis relative to patients that have worse prognosis. So I already talked about gene expression, i.e. RNA-seq. Today, we'll actually talk quite a bit, not just about RNA-seq, but also about other data types. It's not super important that you kind of know in detail how each of these is generated, but it's just important to know that there are various other data types. So the most important one is probably clinical data. So this would just be something like age, gender, maybe what treatment the patient was assigned. So this is typically pretty low dimensional, but we also have things like DNA methylation, microRNA. This is a type of proteomics, CNVs, copy number variation. So there's really various types of this omics data, and they can kind of contain varying degrees of information. And before we get into some of the results, I just want to briefly give you some thoughts on why we think that this multi-omics data is actually, I mean, it's a bit maybe more complicated than it looks, right? Because with all these foundation models today, multimodal integration is a very popular topic, and multi-omics may look like it's just another of these multimodal integration problems, but we actually think that it's a bit different. So in particular, we think the most difficult part is that these data sets are incredibly small sample size, right, relative to something like vision or text, because this is one of the largest data sets that exists really for these type of data. So this is the Cancer Genome Atlas, TCGA. And even in this data set, we only have about tens to hundreds of samples per patient. So the sample sizes are extremely low. At the same time, since biologically all of these modalities are strongly related to each other, of course, we have super high correlation. But despite this, we don't really know what to expect, right? So the information content is extremely different, meaning that a priori, we don't really know whether we should even, when we're doing something like survival prediction, we don't actually know whether we should even include all the modalities, or whether we should maybe just restrict ourselves to gene expression. And lastly, the dimensionalities are very different. So as I already mentioned, clinical data, for example, may just be 5 covariates, something like this: age, gender, treatment, whereas something like gene expression will typically be on the orders of 20,000. Something like methylation can even be on the orders of 400,000. Okay, so that was it for the background. I'm happy to take questions. Yeah, if you have any questions on the background, I'm happy to take them now. If there's questions on the project, I would just take them at the end of each project. Yeah. Okay. So I will now get into the sparsesurv project. So this will be focused primarily on knowledge distillation. So when we started this project, we started thinking mostly about, okay, how do we currently fit survival models in high dimensional settings? Because we were working quite a lot with this type of data, right? Mostly gene expression in the beginning. And then statistically, this is a very typical problem, right? So we have P much larger than N. How do we fit a model like this? Well, we fit them just as we would for regression or classification. So most people would reach for something like a lasso, group lasso, sparse group lasso, SCAD, MCP. I'm not going to list everything, but kind of various high-dimensional regularization techniques have emerged for problems like these, some with better theoretical properties than others. But I mean, if I'm being honest, most people anyway still use the lasso, right? So yeah. And a lot of these have really been adapted for the Cox model and other survival models. And I would say something like the lasso is probably easily the most commonly used technique for a problem like this, even for survival. And then, so we, in the lab, we also do quite a lot of machine learning work. And yeah, we sometimes go to machine learning conferences. And so for those of you that may be more familiar, so in machine learning, also in recent years, kind of knowledge distillation has been kind of a really hot topic, especially with these very large foundation models that you can then maybe distill to a larger model.
It dropped again.
Okay, sorry. Should I maybe try? I'm not sure what I can try. Maybe there's something in the settings. Because I don't see anything. It's very weird. Like okay, well, I don't. I guess I could just reshare.
Would it be possible for you to send the presentation to Diana, or one of us can present?
Yeah, sure. Or maybe, yeah, that's definitely. Let me. Okay.
Oh, I don't know. Did you try sharing just the presentation rather than your whole screen?
So that didn't work for some. So I'm just on the. So I never really use Teams. So I'm just on the browser thing. But for some reason, it doesn't actually show me. It doesn't actually show me the option to share. Maybe I can try with PDF because I was just on PowerPoint. Maybe with PDF, if I share the PDF, does that work? Yeah, that I can try that. Let's maybe try that, and otherwise I'll send you via email the PDF, and then we can go that way. Okay, right. Let's hope that goes better. All right. So where was I? Okay. So we became very interested in the application of knowledge distillation to survival analysis, particular for these high dimensional settings. And as we started researching this, we actually quickly found that people had actually been thinking about this for quite a long time, also in a more statistical setting. So there's actually a paper from 2008, which tries something very similar, but focused on the same problem that we're interested in, namely feature selection, but essentially in a knowledge distillation framework. And so what does that look like for our specific problem, right? So what we do is similar to general knowledge distillation in a machine learning framework. We fit some kind of teacher survival model. So this can be an arbitrary model, right? So ideally, you want some model that is as accurate as possible. So this can be something like a nonlinear Cox pH model, can be a neural network, can be linear Cox pH model on, for example, PCA, can be more or less anything that you want. The only important thing is that this model effectively determines the model class that you're working with. So if you fit a Cox model as a teacher, you also end up with a student model that is a Cox model. And then you basically use the predictions of this teacher model on the training set as a new kind of noise filtered continuous target y tilde. And then we're essentially back in a standard regression setting, right? Because now we can fit, again, any of these high dimensional regularized methods like a lasso, group lasso, sparse group lasso, whatever you want, MCP, but for a regression setting with the target of this y tilde, which then yields some estimated beta hat. And then finally, depending on what we're interested in, typically, as I mentioned in the beginning, we want the survival function. We would still, for a Cox model, for example, need to estimate the baseline hazard to then yield a survival function based on the censoring indicator, time, and R coefficients. So before I get into the results in the paper, just a couple of thoughts on like, why does this even make sense? Are there certain advantages to this? So on the advantage side, I think similar to machine learning, there are actually quite a few. So first of all, it's nice because we actually get to use very efficient new optimization techniques. So for those that are maybe more familiar with optimization, I mean, there's always people developing new optimizers for example, for the lasso, but typically they're not working on survival, right? Typically they're working on regression, sometimes on something like classification, but just because the regression setting is so much easier, both in terms of setting and also in terms of data sets, typically these only get developed for these settings. So we actually get to leverage these even though they haven't really been developed for survival. In addition, we also can actually trivially adapt sparse methods from new model classes. So in particular, this extended hazards model, for example, we can just change the teacher and we actually don't need to develop a sparse model. We don't need to develop a dedicated lasso for the EH because as long as we can change the teacher, the student stays the same because it's just on our regression setting. From a methodology perspective, and this is more empirical now, we actually see that we have significantly increased stability with respect to the regularization hyperparameter, in particular because the teacher performs a sort of noise filtering. This might sound a bit hand-wavy now, but I think if I show you the results in a second, you'll agree with me. And then lastly, so we developed this using the scikit-learn API, and this is quite nice because it enables us to be basically out-of-the-box compatible with other survival packages, such as scikit survival, which is used quite frequently. And as such, we get to use models from packages like this as a teacher, which really make the overall estimation process for users hopefully quite easy. Why does this make sense? So here it gets a bit more complicated, right? So the theory is only moderately well developed, I would say, even in the regression setting. So both in the machine learning community and in the statistics community, while these techniques are more or less relatively frequently employed, it's not really fully clear in terms of theory why this is kind of supposed to work. So in this paper from 2008, the original motivation was via latent variable model, but again, this is restricted to the regression setting. But there has been more and more work in this recently, especially from Bayesian. It dropped again. Okay, I'll send it to you. It's very odd. Okay, so let me just send it like this. So should I send it to you, Liz, or to who?
Either is fine. You can send to me. And
Okay. Okay, I just sent it.
I don't see it, but it just takes a bit of time, I think, before it comes through.
Okay, I sent it to both of you also. Should just be a PDF.
Perfect.
If I send it from a private email, I can also
I find it. Yeah, it's here.
Okay.
1 second. So while I'm sharing, maybe like if you can give like a little bit more like quick example of like how this knowledge distillation works. So like your y tilde y, is it like the outcome of the Cox model? Is it just the
Yeah, exactly. So it would essentially be the linear predictor of the Cox model. So essentially just the predictions
the
of the
linear
Cox model.
predictor?
So,
Okay.
exactly. Yeah.
Using
So in machine learning,
all the features without any preselection.
yeah, I mean, so it depends a little bit what you fit the teacher with, right? So, I mean, you could also use a teacher that uses some kind of feature selection, but we've found best results by just using all features or using something like a PCA before you fit the teacher. But I mean, yeah, in machine learning, there's a lot of kind of disagreements on things like this, right? So I guess, and I mean, this will also be one of the limitations that you need to have a good teacher, otherwise it doesn't really work.
Okay, so let's find where we stopped.
Yep. Right.
Here.
So I think it was maybe here. Yeah.
Yeah.
Yeah. Maybe the slide after. Yeah. So as I was mentioning, there has been more and more work on this in recent years, especially from a Bayesian lens. So I think from that perspective, maybe it's also can be some hope that there will be more, more theory on this also in the future. Okay, so now let's get to some experiments. So we ran experiments for this on 10 commonly used TCGA RNA-seq datasets. So again, TCGA is this the Cancer Genome Atlas data. So this is this very large-scale bulk RNA-seq, among other things, datasets. So in particular, we're using 10 datasets that are among the largest datasets from TCGA. In this example, since we're just focused on unimodal setting, we're doing RNA-seq data only. And we're doing 20,000. So as I mentioned, this is roughly 20,000 covariates per data set, because this is about the number of protein coding genes that we have. And then we have 100 to 1,000 samples per data set. So as I said, this is a typical P much larger than N problem. Okay, the first thing that we were interested in, this is also one of the main motivations, I would say, for knowledge distillation, is that knowledge distillation can actually improve runtime quite significantly. So we're showing 4 models here. So we're showing a typical GLMNet model. So this is a lasso. I guess most of you are familiar with this. We're also showing a tuned GLMNet model where we tune the elastic net trade-off parameter. And then we're showing 2 knowledge distilled models. One that is simply based on a linear teacher with PCA, and then one with a so this is in pink, KD Breslow, and then KD Cox neural net is essentially a teacher with a neural network that is then also distilled to a standard lasso. And we see that while the neural network teacher is somewhat slower than a standard GLMNet model, but this is really mostly because of the teacher. The KD Breslow model is still about twice as fast in most data sets compared to a standard GLMNet model, and this can be increased even further depending on what teacher you choose. And yeah, from that perspective, it's quite flexible. It can be run super fast, and I think in the future this delta in terms of runtime should only increase, because you get to always use the most novel regression method for optimization. Whereas, as I said, so GLMNet, there has been, I think people pretty much almost exclusively still use GLMNet just because most packages that implement the lasso or something similar typically don't implement the Cox model. Okay, I think this is really the main takeaway, and this is what I was talking about with the noise filtering. So distillation really improves stability with respect to the regularization height parameter. So we have this Antolini C on the y-axis here. So this is this discriminative performance metric. And then we have the regularization index on the x. So this is from sparse to dense, which means that 0 is essentially fully sparse, and 100 is essentially the least sparse. So this would be approaching essentially the number of samples in the lasso. So this is a typical lasso or elastic net path for those of you that are familiar with that. And then we have in blue, again, a standard GLMNet model. And in pink, we have, once again, our student that is distilled from a linear teacher with PCA applied to it. And then we also show a dotted red line that just shows the performance of the teacher. And we see that while the performance of GLMNet is quite variable across the regularization path, and they can be often something like a local optima. So for example, on kidney, we see, so this is Kirk, we see, for example, that the performance of the GLMNet model quickly dips above the performance of the student and teacher, but it's really very variable. And in practice, it's actually very hard to kind of pick this point properly, right? So you'd typically pick this with cross-validation, but that doesn't actually guarantee that you kind of hit a good point. But I'm not even trying to make the point that this somehow outperforms, right? I'm rather just making the point that this is super stable, right? So the performance of the student is not really dependent on the sparsity. So you can more or less pick the sparsity as you want, and you still get quite good performance because the teacher does some kind of noise filtering, right? So it's much harder to overfit here just because the teacher kind of takes care of the overfitting issue. Okay, and then we have a comparison in terms of, on the right, we have the number of non-zero covariates, so this is sparsity, and on the left, we once again have this Antolini C, so this discriminative performance measure. And we see that while the standard GLMNet model performs somewhat worse than the tuned GLMNet model and the three students here, it also is significantly sparser, right? So we see that this blue student on the this blue GLMNet model on the right is really much sparser than all the other models. But we actually see that when we pick a different way to choose the regularization hyperparameter for the student, we can actually get a similar level of sparsity while still increasing performance. And again, I think if you look back at these regularization hyperparameter plots, this makes sense because you didn't really see a big impact on the performance of the regularization hyperparameter that you pick. So you can achieve relatively high sparsity levels while sacrificing little to no performance, just because, as I said, the overfitting is much less of a problem because the teacher performs this kind of noise filtering. Okay, so just to summarize the distillation project. So we know that this kind of knowledge distillation, so I put a bunch of slashes here just because this is, I think, a typical thing where people in machine learning use a different word than people in statistics, right? So people in statistics might call this reference models, preconditioning, and people in machine learning would typically call this knowledge distillation. But so we've shown that this works relatively well for estimating sparse semi-parametric survival models. In particular, we've shown decreased computation time, applicability to a Cox model, or also to something like an EH model. And I think most importantly, greater robustness with respect to the choice of the regularization hyperparameter. But I think there are still some drawbacks. So as I mentioned already, theory is not really well developed, especially in the survival setting. And I mentioned this previously, the performance is more or less fully dependent on the teacher, right? So if you don't have a good teacher model, you won't have a good student model. So of course, this is some drawback since you need a priori, you need to have a good model to fit as a teacher. Otherwise, it just will not work. Okay, and since we've lost some time with the turning on again, I think maybe I will skip some parts of this, but maybe we can do the intro and then we can skip to some of the results. So the second project is a benchmarking project for multi-omics cancer survival analysis. So in particular, we started working first on unimodal cancer and then on multi-omics cancer. And so as I said earlier, this is data from the Cancer Genome Atlas project from TCGA. And this is actually also the 7 modalities that we personally use. So clinical data, RPPA, microRNA, DNA methylation, gene expression, copy number, and mutation. So if we looked at these papers, and maybe we could go to the next slide. We identified a few problems. So the first is that there's an extremely strong focus on TCGA. So I think that makes sense on the one side, right? Because as I mentioned, this is really the only project that offers this depth of data sets and all these different modalities. But nevertheless, there's a pretty strong risk of overfitting because what happens is that, well, everybody trains on the same 10 data sets, and then the benchmarks also benchmark on these same 10 data sets with hyperparameters that have often already been cherry-picked in the original paper. So there's a very real risk of overfitting to TCGA here. In addition, there's a pretty extreme lack of standardization. So in survival, there's really, I would say, a lot of choices in pre-processing. And it's not like something like in machine learning with MNIST, where you get a relatively standardized data set already. Instead, you get more or less the raw data. So you start with more or less maybe counts. And then for RNA-seq, and then you need to actually decide, okay, do I impute this? Which patients do I keep? Which samples do I keep? So it's really a lot of choices. So we just picked out 2 papers here that are a bit older, but exemplify this pretty well. And so here, there's a difference in terms of the data sets, the endpoints. So for example, in survival, you can model either the overall survival or disease-specific survival. There's also other types. Also, the omic data and other things can often be very project-specific, meaning that if you get good performance in one paper, that doesn't necessarily equate to good performance in another paper, just because so many pre-processing steps can be different. And lastly, and I think this is one of the most important points, although it's a bit subtle, is that models of different types are not always compatible in validation. So in particular, and with these multimodal models, what we see is that sometimes we get one modality that is fully observed, as we see for modality A here, and then one modality which is only partially observed, as we see here for modality B. What some people then do is they say, well, other models in the baseline models actually cannot handle this missing modality B, so I'm just not going to compare to anything because my model is the only thing that can handle this. I don't mean to call anybody out here, but I just think it's a bit unproductive to just say, okay, we can't compare to the literature just because they can't handle this. So we also think it's important to construct a benchmark that actually is built to enable comparison between all different types of models that exist. Right, so our goal was essentially to design a benchmarking approach for multi-omic survival analysis that, as best as possible, fixes these issues and enables comparison of arbitrary model types, and hopefully via the usage of an online leaderboard, also at least encourages future extensibility of the benchmark. Okay, and I think this is the main slide, and after that one we can maybe skip to the results. So the main thing that we did is that we collected 28 multi-omics data sets, so from a total of 4 projects. So I already mentioned that TCGA is the most commonly used one, and actually TCGA still accounts for the majority of data sets in our benchmark. So we have a total of 28 data sets, and 20 of those come from TCGA. But nevertheless, we think it's important to also include things like ICGC, Target, and MetaBrick, just because then you can still stratify, for example, on the project and see, okay, do we get a different type of performance on TCGA than we do on MetaBrick, than we do on ICGC. So even if it's less data sets, you can still basically look at them separately and via that essentially guard against overfitting. And then we also have pretty standardized pre-processing. I won't go into details here, but we do things like requiring, okay, we require at least 10 events per data set and at least 100 samples in each data set. And lastly, also we require that both clinical data and at least 2 omics modalities per data set must be present, since otherwise we wouldn't really be talking about multi-omics. Okay, and then I apologize that we have to skip some parts, but maybe we can skip to, yes, yeah, to here. So I want to just show you 2 results, really. So one thing that is less of a result and more of a pitfall. So again, as we were reading papers, we noticed a couple things that I think even if people don't end up using our benchmark, we thought were kind of important to point out. So one thing is cherry picking metrics. And I guess a lot of people have seen this before. And what we see on the left is really just a correlation matrix of the different metrics. So we have the central linear C, the integrated Breyer score, and decalibration. And as I mentioned, decalibration is essentially fully orthogonal to antilinear C, right? So we have a correlation of minus 0.07, so essentially nothing, meaning that you should really report both of these metrics, right? Because essentially, just because you're good in one metric, it says essentially nothing about your performance on another metric. And this is also what we see in the data sets, right? So if we look at this on the right, this is the MetaBrick data set, and the metrics are all scaled here such that lower is better. And we see that while in terms of antilinear C, we see some of these neural networks, so NN just denotes neural network, we see 2 of the neural networks performing best. But when we look at the integrated Breyer score and the decalibration, which are also driven more by calibration, we see that priority lasso clearly outperforms everything else, right? So, and we just wanted to make the point that it depends, of course, what you're most interested in, but in general, it doesn't make sense to only report one metric, because it can easily happen that your model is good in one metric and terrible in another. Okay, I think this might also be quite interesting to some people. So the second pitfall is very small cross-validations, or particular not repeating cross-validations. So what we did here is we perform a cross-validation, and instead of just performing it once, we repeat it 5 times, and then we show the ranks in terms of interlinear concordance on each of the cross-validations, as well as overall. So overall is denoted with all. And then basically rank 1 is the best and rank 6 is the worst. And this is just ranked across these 6 methods that are shown here. And then in each of the facets, we have one data set. And essentially, we see that the performance is super variable across cross-validations, right? So even in relatively large data sets, such as breast cancer here, we see flips that go from rank 5 to rank 2. Or if we look at this data set on the very left, we see flips that even go from rank 2 to rank 6. So it's really extremely variable depending on the seed of the cross-validation. But if you look at the all column, you see that this is some kind of aggregation, of course, because we're just calculating across all the cross-validations. And this is, of course, much more stable, right? So again, this might seem a bit trivial, but we've seen a lot of papers where people sometimes don't even do a cross-validation, but do a single validation split, which can be fine if you have a very large data set, but these data sets are tiny. So you really need to repeat your cross-validation at least 5 times, ideally even more often. Okay, should I finish up or?
Yeah, I think because we want some time for questions, so maybe, yeah. Do you want to just like sum up quickly? Or
yeah. Can you maybe go up to the Outlook? So one, yeah, here. Yeah, so sorry. So this ended up being a bit rushed, but I think overall, this kind of field, so both multi-omics survival analysis and also single omics, so let's say gene expression only, they offer very interesting and very hard statistical applications. But I think one of the biggest problems continues to be data. So especially for multi-omics, data set sizes have grown quite a lot, but they're still very small. And currently, and so we ended up skipping that, but actually, when you do the benchmark, it turns out that most of the modalities essentially offer no predictive value beyond just clinical data and gene expression. And it's kind of unclear whether that's just because most of the information is actually clinical data and gene expression, or, and what's probably more likely is that also that we just don't have enough data to really learn with all of this very high dimensional, high correlated data. But unfortunately, I also don't think we will get much more data just because the bioinformatics community today, they are much less focused on these bulk data sets, which we would need for problems like these, and more money and consortia are rather doing single cell, well, or even spatial and long reads. So I think it's kind of a shame, but currently the data is really the most limiting factor. And then maybe we can just go to one slide down. Yeah, and then just to say, I'd like to just thank my labs, both of my labs, and also collaborators at IBM. And lastly, of course, most importantly, the patients and their families that ended up donating their data, and the 4 consortia that we're using the data off here. And of course, thanks a lot to all of you. Apologies again for the technical issues and the rush, but thanks a lot for listening. And yeah, I'm happy to take any questions or discuss anything.
Thank you very much, David. That was amazing. I think we, at least I have like few questions, but maybe if someone else wants to go first. Sure. Okay, let me ask. First question is basically, so because you worked a lot with Cox model, what I found is that there are some subtle limitations with Cox model, is that it's like primarily based on like rank statistics and things.
Yeah.
So perhaps the temporal data is not ideally captured by that. So did you find, or like any solution, did you try to think about this? Yeah.
Yeah, so I think there's a couple of aspects to this question. So I agree that I think in a lot of cases, the Cox, like the bias that you impose with the Cox model is like very strong. And I think often it's kind of unrealistic. So I think for this type of data that we're talking about today, I think the reality is that since the data are the sample size is so limited, in most cases, you can't really get much better than a Cox model, just because the dimensionality is so large. So we've really benchmarked kind of various model types on this task, and we've never really gotten something that really significantly outperforms a Cox model. Mostly just, we think, because the sample size is so tiny and the dimensionality is so huge that it's kind of really just hard to learn anything, or not anything, right? But it's very hard to learn more than like a relatively simple type of thing that a Cox model could also learn, namely that, okay, this patient ranks higher than this patient. But I agree that I think for more like further data sets that people work with more in machine learning applications, so where you have lower dimensional data, so clinical only data with maybe a few thousand samples, there I fully agree that the Cox model, and I also actually think that the Cox model, it's always portrayed as very interpretable, but I think really for clinicians, it's not actually that interpretable, because you really always have to think about this hazard functions level. And I think even just explaining to somebody that isn't a statistician, okay, what does this hazard function even really mean, isn't really so easy.
Mm-hmm. And yeah, and another question that I had, that perhaps that when you mentioned that calibration, so it, like we pretty much agree with like many things that you've said, and I think that in our prediction modeling group we also try to advocate for diligent validation of every model. Like in fact, our latest package was actually like doing multiple data splits, like repeated cross validations for like Cox model versus survival Cox versus deep heat versus other things. Performing like statistical, and we did find that like Cox model is really hard to beat in many data sets. But like with respect to calibration, though, I find that like sometimes when people say that neural networks, they're like worse in terms of calibration, I think it's a little bit by design, because like design of Lasso Cox model is like you actually design things which are linear with the chances of like with the prevalences or observed frequencies that you see. So that's why it's kind of naturally well calibrated. And for neural nets, I saw some post calibrations where you find when you do that, so perhaps that will be like a more fair comparison, because if you didn't design to have like a good calibration, you probably wouldn't have it, you know.
Yeah, fully agreed. I mean, I agree. Like, I think it's very similar to like classification tasks, right? Because there you've seen the same thing, that basically, okay, it turns out that neural networks just after training are miscalibrated, but it's relatively easy to fix either via post-hoc calibration or also with kind of auxiliary losses. I think our point wasn't even so much that neural networks are worse at calibration. It's just that like we were a bit just like, please just report calibration, like just because some people will just like not report it and then just act like, oh, like neural networks are great for everything, and it's just not really the reality. But I mean, I fully agree in general that I think post calibration is super interesting. I think in general, calibration for survival, I think, is a very interesting and pretty underexplored area.
Any more questions, Miriam?
Yes, hi, thank you. You talked about cross-validation, and actually I'm finding that I have to constantly convince people of the need for cross-validation. I have been accused of doing far too many folds of cross-validation. So I tend to do, instead of doing 5 folds, I would do 5 folds 3,000 times and then see how many times I get concordance and extract those for feature selection. Do you think that, have you seen a limit to how useful cross validation can be?
So I mean, I've heard a similar question. So I think, I think something like what I think is a good number of repetitions is something like 25 if you have the compute. I think really something like 5 is really the bare minimum. I think doing more than 25 is great if you have the compute, but we haven't really seen kind of major differences beyond doing like 25 versus 50. I think something that in that vein that's also a bit underappreciated is actually the number of folds, as you mentioned, because in survival, I think it's actually also important not to do too many folds. And I mean, not repetitions, but folds. So I think, for example, in survival, especially in these small data sets, it's quite risky to do something like a 20-fold cross-validation, because then your evaluation sets become very small and the metrics are pretty much only driven by the events in the test set, right? So if you have these very small test sets, your metrics become very noisy to calculate, just because you're calculating like a metric with maybe 3-4 events. So I think it's also important that not only do you repeat, but you don't make like 20 folds or something, just because the data sets I think are too small for that.
Excellent, thank you.
Thanks.
Any more questions, maybe?
Yeah, I was going to ask something if
Yeah.
no one else has a question. So we deal with massive correlation and overfitted models in genetics on a daily basis, and it's actually one of the things that really slows down real discovery, I think. Some of it, obviously, we can navigate by. So, for example, in genetic data, you could do a very severe pruning of the data and reduce linkage disequilibrium in the data set that remains. But I wonder how something, i.e. biologically informed pruning and essentially reducing dimension, compares to a completely agnostic model obtaining for sparsity.
I think very good question. I think kind of hard to answer. I think in general, I'm personally a bit of a fan of building very simple models, because like what I've seen is that a lot of people want to build, let's say, a multi-omics model for survival, just because like it sounds cool and it seems like throwing all the data in there would be useful. But I think especially with biological data and kind of omics data, the reality just is that the data is super noisy. And most of the time, the sample sizes that we have are just too small to justify this kind of machine learning. We're just going to throw everything into a linear algebra and then hope it works out. So I don't know. I think that's kind of, I mean, this may be a bit over the top, but that's kind of, I think, my thought that like, I think people should start way smaller. And I think in a lot of bioinformatics scenarios, it's like you don't need multi-omics data for everything, right? So I think just starting with the modalities that are kind of the most predictive has served us very well. So I think these days we really think primarily about models that incorporate clinical data and maybe gene expression, and anything beyond that, we're really kind of like, I mean, I'm not saying it's not possible that it will work, but it's just, I think it needs a lot of work. And I think beating like the smart prior of somebody like a clinician or a biologist, I think in these scenarios, it's not very easy unless you have a lot of data. I think as soon as you start having a lot of data, and this is kind of what you start seeing, I think now with some of these foundation models for single cell, although they also don't all work great yet, but I think that's what we start maybe seeing there, right? That once you cross some data threshold, maybe you start being able to kind of just make sense of the noise just via pure data amount. But for something like survival, I just don't think we're anywhere close.
Yeah, thank you.
Thanks.
Thank you very much. I think that's really good, and that's really insightful in many ways. I really enjoyed learning about the how you employed knowledge distillation for survival analysis, and how you accommodated different extended Cox models as well, and how you performed both. How also I really enjoyed the way that you presented that instability, like how you can see like in different faults. And I think if you go inside the faults, it's even more random.
For sure.
So you could definitely see the benefit of like repeating it and having more stability. So thank you very much. I think we're gonna finish on time. So yeah.
Perfect.
Thank you.
Okay.
Thank you. Bye.
Okay, thanks a lot. Thanks a lot for the invitation.
Yeah, David, maybe if you
sure.
stay a bit, I could ask some more questions.
Yeah, of course. Yeah, sure.
Yeah.
Thank you, everyone.